Hey everybody, welcome back to chemistry. And so now we're moving into a new chapter, chapter 8, which is about solutions. And so with this presentation and some of the ones that succeed this, I'm going to be talking about some of the qualitative properties of solutions. In other words, we're going to talk about properties of solutions that can be described with words. And then once we're done with that, then we'll look at some of the quantitative properties of solutions. There, we need numbers to describe these properties, and most importantly there, we're going to start thinking about how do we figure out what the concentration of a solution is, which is extremely important. So if I can increase the slide. So the first thing I want to do is I want to understand where solutions are in this scheme by which we classify matter. And so here at the top of the scheme we have matter. And then on the left side here, we have pure substances. And you might remember there are two kinds of pure substances, which are either an element or a compound. And all pure substances have the same composition no matter where you sample it. But on the other hand, you may have two or more pure substances mixed together. When you have that happen, that is called a mixture. And so, as you probably know, you can put one pure substance into another and vary the proportions. If you're able to do that, that classifies it as a mixture. Now, what we can do is we can subdivide mixtures into two types. So one type is something called a homogeneous mixture, and so that is on the right side here. So we have a homogeneous mixture here. A homogeneous mixture, as you might remember, is a mixture where you have two or more pure substances and they are so well mixed together or they're so well dissolved in one another that if you're looking at that container of that mixture, if you sample it various places, it will have the same properties throughout. We'll talk a little bit more about that in a minute, but here I want to point out that a homogeneous mixture is a solution. So most of this presentation will be about solutions which are homogeneous mixtures. Now, there's another kind of mixture which is on the left side here, which is called a heterogeneous mixture. So a good example of that is if you dump sand into water, and you probably know that the sand will not entirely dissolve in the water. You'll have a little bit of sand that dissolves in the water, but a lot of the sand will not, and will just settle to the bottom of the container. And so one of the things you might expect is that where you sample it sort of determines the properties of that mixture. So if you're sampling here toward the top of the mixture, you get mostly water, and so the properties will be more water-like. But if you sample here where the sand has settled, then the properties will be more sand-like. And so that's what a heterogeneous mixture is that you have pure substances that don't dissolve well with one another, and then because of that, that mixture will have different properties throughout it. Okay, so here I'm just restating something I said earlier, that all homogeneous mixtures are called solutions. So the example I kind of mentioned earlier is this one. When sugar is dissolved in water, the sugar seems to disappear. We then observe a clear liquid throughout the mixture, which looks the same throughout. That makes it a homogeneous mixture. So it is a mixture because we have two or more pure substances dissolved in one another, which are water and sugar. But it is homogeneous because wherever we sample this mixture, it has the same properties. For example, it will have the same density, the same boiling point, and so on. So let me explain that a little bit. So imagine here we have a container, and in this container is water, and you have dissolved some sugar in it. So just to remind myself here that there is sugar dissolved in the water, I'm going to put little dots here just to remind myself that this is a homogeneous mixture or a solution of sugar and water. So if you were to sample here, for example, what you would find is that the sugar water solution would have a certain density. And so, in fact, one of the things you'll learn is that when you dissolve things like sugar into water, you can increase the water's density. So maybe the density is like 1.25 grams per mil. And then maybe you're able to measure the boiling point of that sample, and what you'll discover is that the boiling point of sugar water will be higher than that of pure water. And so maybe the boiling point of this is going to be 103 degrees Celsius for a boiling point. So the thing is it doesn't matter where you take the sample. You can take it there, or you can take it from there, or you can take it from there, or you can take it from there. Wherever you take the sample of sugar water, it will have exactly the same properties. And if that's the case, that is what makes it homogeneous. So a couple of vocabulary words which you must memorize. The component of the solution that is estimated to be in the minority amount is called the solute. If you have a component in the solution that is estimated to be in the majority, it is called the solvent. And so in the sugar water example I was just talking about, you can imagine we probably don't have nearly as many sugar molecules dissolved into the solution as we have water molecules. And so sugar is probably the one where we have the least number of molecules in a sugar water solution. So the sugar will be the solute. On the other hand, the solvent is going to be the other pure substance component. We have a lot more of it, and so that will be water. Now, one thing to keep in mind is that the solute plus the solvent is the solution. So in my example here, the solute was sugar, the solvent was water, and so the solution is sugar water. So not all solutions are where you have a solid dissolved in a liquid. Remember, any homogeneous mixture is a solution. So here's an interesting example. Think about what air is. You might know that air is comprised of many different pure substances. And so the major component of air is nitrogen gas, but that's only about 78% of the air molecules. Another 21% of the air molecules are due to oxygen, and then you have around 1% due to argon, but then there are other molecules dissolved in the air, such as carbon dioxide and water vapor. So what I'm hoping you can see is that air is definitely a mixture, but if you imagine a sample of air, it's pretty much going to have the same properties wherever you sample it. So it is a homogeneous mixture. So because it's a homogeneous mixture, it is a solution. And so we have this described here. So here is a solution, which is air, and the solvent in air is nitrogen. And the reason is because we have a lot more nitrogen molecules than any other pure substance in the air. One of the solutes, maybe the primary one, is going to be oxygen gas, but as I just told you, there are other solutes that are dissolved in nitrogen. So for example, argon and carbon dioxide and water vapor and things like that. Okay, so probably the solutions that we're sort of most familiar with are solids dissolved in liquids, and so that is right here. And so for example, they have the example of seawater, and so in seawater there are very large amounts of sodium chloride dissolved in the water, but the sodium chloride ions are much less in number than the water molecules, and therefore the sodium chloride ions are solids and the water is solvent. And of course, you know, in seawater there are a lot of other different ionic compounds dissolved in seawater. Now, there are other things that can be called solutions. And so, for example, another kind of liquid solution is where you may have a gas dissolved in a liquid. And so a great example of that is a can of Coca-Cola. So with Coca-Cola, you of course know that there's a lot of sugar dissolved in the water. So that would be a solid dissolved in the water. But maybe one of the other things you may be aware of is that there's a lot of gas dissolved in the water of Coca-Cola. That gas is carbon dioxide. That carbon dioxide is pretty evenly distributed throughout the water in Coca-Cola, and so it's essentially considered to be a homogeneous mixture, and so it is a solution. But then there's some really interesting ones down here in solid solutions. So I have, unfortunately, a bunch of solid solutions in my teeth. What those are dental amalgams. And so what a dental amalgam is silver that's been melted in with a little bit of mercury. And so that will be a solid solution because the mercury is just randomly distributed about the silver. And so you can sample the amalgam and you'll find it'll have the same properties wherever you sample it. And then there's some other examples of solutions that I didn't go over. Now, another thing you need to be aware of is you can classify solutions in terms of the size of the solute. And so here when we do that, we range from solutions where the solute size is very small, all the way up to suspensions where the solute size is very large. Then we have something in the middle called a colloid. So let me go over that. So you probably have seen a solid dissolved in the water, which is a solution. So for example, if you dissolve all sugar into water, that is a solution. So here, the water is the solvent, the sugar is the solute, and as you can imagine, the molecules of sugar are extremely small, and so they're going to be less than 1 nanometer in size. And so if that is the case, then here the sugar molecules are thoroughly dissolved in the water, and there's really no way that you can easily separate the sugar from the water by some kind of physical process. So for example, you cannot separate the sugar from the water by filtration, nor could you separate the sugar from the water by regular centrifugations. Now, on the other hand, on the other side of the scale here, we have heterogeneous mixtures, which are suspensions here. And the reasons why they're suspensions is because now the solute particles are relatively large. They're about a micrometer in length. The particles are so large that they can no longer dissolve into the water. And if they can't dissolve into the water, then gravity can work on them and pull them down. Now, when you have a suspension, again, imagine, say, sand and water, which is, again, is a heterogeneous mixture. Yes, you can separate the components of the suspension by filtration. And also, you might be able to separate the components by centrifugation. So an interesting example of a heterogeneous mixture or a suspension here I haven't mentioned here is blood. So imagine taking out blood from your vein and looking at it, say, in a container. So it kind of looks like it might be a solution, right? But what's interesting about blood is not only are there salts well dissolved in the water of blood, but there are actually a lot of cells in the blood, which are red blood cells, white blood cells, and platelets that really in no way dissolve in the water. In fact, what they'll do is they'll settle out from the blood solution if you wait enough time. So blood is considered a suspension. So blood, you can remove the cells by filtration or you can remove them by centrifugation. So it kind of raises the question, is there sort of an in-between place between solutions and suspensions? And the answer is yes. If you have particles of an intermediate size, then you could have a colloid. So I think to imagine a colloid, the best way to imagine that is by thinking of a good example of that, which is milk. So milk is a wonderful example of a colloid. So you probably have seen milk, and you can see that it's not transparent. So that might suggest that this is something other than a solution. And so here, the reason why milk is not transparent is because the particles in milk are not fully dissolved. The particles here in milk are fat droplets that contain protein. So they are fairly small, but not so small enough that they can dissolve well in the water. So these fat droplets that contain protein, the reason why it appears cloudy is because these droplets do a great job of scattering light. And when you have material that does that, then it appears sort of a whitish, opaque appearance. So in this example of a colloid, which is milk, the particles, again, are sort of intermediate in size. And so the particles are small enough that they cannot be filtered out, nor can they be centrifuged out. So you really cannot put milk in any kind of centrifuge that is around in a lab and spin it so fast that we can get those fat droplets to settle out. But the particles are still kind of large in the sense that they do scatter light, and they really can't be called a solution. So now what I want to do is kind of generally talk about what solubility is. And so when a solute is soluble in a solvent, that means all the solute dissolves in the solvent. So some examples of this we have already talked about. So for example, if you have some salt and you're able to dissolve that in water, we say the salt is soluble in water. If you have sugar and you're able to dissolve all of it in water, that is said to be soluble in water. But then, for example, you can have ethanol, which is a liquid, and it will dissolve readily in water. So ethanol is soluble in water. On the other hand, if you have some kind of solute that does not dissolve in the solvent, then it is not soluble, or the word we use is insoluble. So a really good example of that is, imagine oil in water or oil in vinegar. So you probably know that those will separate out if left standing, and there will be no vinegar dissolved in the oil, nor will there be any oil dissolved in the vinegar. Same thing with oil and water. And so you would say that oil and vinegar or oil and water are insoluble. Okay, there's some basic solubility rules that you need to know. One you're probably already aware of is this one. It's when you have a liquid mixed with a liquid, the rule is like mixes or is soluble with like. So as we talked about before, polar molecules are soluble with other polar molecules. So for example, you can mix ethanol and water together. And then we also talked about how nonpolar molecules are soluble in other nonpolar molecules. And so here I have a picture of that. Here we have a beaker, and we have here a solution, which is a homogeneous mixture. So on the left side here, we're pouring in this one nonpolar molecule, which is called carbon tetrachloride. And then on the right side, we're pouring in another nonpolar molecule, which is called octane. Those are both liquids, and they mix well together, so they're soluble within one another. And it's because they're both nonpolar molecules. Now, one thing you're probably already aware of is that polar molecules are not soluble in nonpolar molecules. And so the wonderful example of that is oil and water. So up here we have oil, which is nonpolar, so I'm going to write NP. Here we have water, which is polar. So you can mix away, but if you let it stand for any length of time, then you'll discover that the oil will separate from the water, and you'll see absolutely no oil dissolved in the water. And so you would say that oil is not soluble, or it's insoluble in water. So there are other things you need to be aware of. You need to be aware that ionic compounds dissolve in polar solvents like water, but not all of them. And we're going to talk a little bit more about that in another presentation. Another thing you need to know is that all ionic compounds are insoluble in nonpolar liquid solvents. So what that means is you cannot dissolve an ionic compound like table salt, which is sodium chloride, and say this nonpolar compound up here, which is carbon tetrachloride. Okay, well, thank you for listening, and we'll see you next time.